Precalc 1.4 day 2. We're going to pick up where we left off. Now, yesterday we were talking about all of this maximizing and minimizing of our functions. And the reason is because really what it comes down to is we are maximizing our optimizing our functions. Because as we'll find out when we start to get out in the real world, people want to maximize production, maximize profits, but they don't necessarily want to maximize their costs. They want to minimize those. And what happens is that you got long, complicated problems with the fact that you need to tie all of that stuff together, from wages to production ability, from profit on each item to demand, supply. All of those things get wrapped up into certain equations sometimes. And we try to contrive or figure out some function that it follows so that we can maximize it. Because obviously it all comes down to maximizing profit, minimizing our costs. And so that's what we do here. So in this particular problem, we are going to maximize the volume of a candle or a candle holder. So it says that there's a glass candle holder in the shape of a right circular cylinder. It has a bottom and there's no top. It has a total surface area of 10 pi square inches. I don't want the maximum volume it holds. I actually want the radius and the height of the candle holder that will give me the maximum volume. So, I'm looking at this saying, first of all, I need to know some background information. I need to know what the heck is a circular cylinder. A circular cylinder is just it's a can. Circular cylinder. It's a cylinder with a circular base. Okay? Now, it also tells us that it has a total surface area of 10 pi. So we probably should know what the surface area of a circular cylinder is that has no top. Pi r squared would definitely be part of it. Because what is pi r squared? Area of a circle. And the circle is the bottom of the can. But would you guys agree that that can is made up of a bottom and... No, because there's no top. No top in this one. It's also made up of a rectangle. How many of you guys have ever taken your label off of your jar or your water bottle? Yep. When you stretch it out, it forms a rectangle. So that's the same thing if I took the can and I cut the top and the bottom off and cut down the side, I could roll it out and I would form a rectangle. The height is still the height of the whole entire wrapper or the can. But what is the length of that wrapper? If I rewound it back up, it would actually form a circle around the top. Right? Look at the can. It's a circle on top. And I cut that out and roll it out. It's the distance around the circle, which is the circumference. Perimeter? Circumference? Does anybody know the perimeter of a circle?
Oh, yeah, r squared?
It's in your planner.
I don't need it in my planner.
2 pi r.
It's not saying squared.
So, 2 pi r times h plus pi r squared would be the surface area of that object. Can you guys agree with this? I take all the areas, add them up. We also have to know the volume. What's the volume of any prism?
No, 1/2 base times length.
That would be area of a triangle. What's that?
Pi r squared times height.
It's pi r squared times height. Pi r squared h, because pi r squared is the area of the base, and h is the height. Area of the base times height, AOB times height, is the volume of anything. If it's a rectangular solid, it's length times width times height, because the base is a length times width. It's a rectangle. So, what we have here is we have two formulas that we somehow have to mash together to maximize. I want to maximize the volume. And if I want to maximize the volume, I really don't care then for surface area, right? But the problem is that if I look at volume, volume itself I don't know, the radius I don't know, and the height I don't know. That's like three variables in an equation. We're used to graphing like y equals some x's, or two variables. I put in one variable as a number, I get the other one out. But I don't have ones that have three variables in it. So we look back at our information, and it actually tells us a number. 10 pi. 10 pi is the surface area. So wait, this is equal to 10 pi? So I can really kind of get rid of this idea that surface area's label is not there anymore. So 10 pi is equal to pi r squared plus 2 pi r h. I want to somehow preserve volume, V. I have an r squared and an h. I also have another equation with an r and an h in it. Can I solve for r or h in that top equation and sub it into the bottom?
Yes.
And when I do that, will I get rid of one of your variables? Yes. Which variable in the top equation looks like it'd be the easiest to solve for? R by itself or H by itself? I'm going to say it's H because there's only one of them. If I chose to do R, I would have to be able to get R completely by itself, and I don't think I can do that with an R squared and an R. So what would be the first step in getting that H by itself?
Divide by 2 pi r.
I'm not going to divide by 2 pi r yet, because there's other things there. I'm going to subtract the pi r squared. Subtract pi r squared from both sides.
I didn't even know that was part of the count. Part of what's going on.
2 pi r h equals 10 pi minus pi r squared. And now, Ish, what?
I didn't even know that part was part of the equation.
Divide both sides by
2 pi r.
2 pi r.
That was just part of the scribbles.
So I've just solved for h. Hey, that's pretty cool. Now, when I'm looking at that, it's cool that I was able to get h by itself, but if I'm looking at what h is equal to, does that even look cool at all?
No. Yeah.
That looks pretty scary, right? So is there some way potentially of simplifying that?
Maybe.
Is there something that I can take out of the top and bottom?
Probably.
2 cannot go out because 2 is not in the second half of the numerator.
3 pi r.
But I think there's a pi in everything. So I could technically factor a pi out and then divide it out. Do you guys see that? So h equals pi times 10 minus r squared all over, put the pi out front, 2r. Pi's will cancel, leaving me with 10 minus r squared all over 2r. Hey, that's a lot better to look at than have the pi's in there. Okay. Now what should I do with that H?
Plug it into
Yeah, I'm going to take this expression and I'm going to plug it into here. And when I do that, effectively, I just got rid of what letter? H is gone. I'm left with just R's. V equals pi R squared times 10 minus R squared all over 2R. Ooh! Can I simplify this thing a little bit now?
yeah. The R squared. Right?
Is there anything on top and on the bottom of this? Is an R. Do you guys hopefully recognize that this would be really pi R squared over 1?
Yeah.
And then I'm multiplying these two fractions. So therefore, I could go back and say, hey, I can get rid of this R and that square. So V is equal to pi R times, 10 minus R squared all over 2. It's nothing really nice. I don't think it's like super pretty of any sort, right? But
How do you get rid of the R on the bottom?
Because the R
I canceled the R squared on the outside of the top.
So you just left one, it's R squared.
There was 2 R's up here, R squared.
And it's multiplying?
Yes, because this is multiplying, so you'd multiply the tops, multiply the bottoms.
Gotcha.
Now, here's the thing. I now have an equation only in terms of one variable. Could I maximize that? Now, under normal circumstances, if you were given an equation, you don't have V's and R's. You have X's and Y's. Which one's the X, which one's the Y?
V is Y.
R is X. So really, you guys would normally have seen this.
Wait, why did R turn to X?
Because it's normal.
Oh.
Because if I had to put this on my calculator, because that's what I'm going to ask you to do now, is take your calculators out, take your graphing calculator, and graph that. Pausing the video for it. Ladies and gentlemen, come back here. Our graph, guys, I do believe something like this. It's going to be moved left, right of your axes. I'm not exactly sure because I don't have it with me. But you guys should be able to see that there is a high point of your graph, relative maximum, and a low point, which we call the relative min. Local max, local min. Now, we don't care about minimizing the volume. We only care about maximizing. So, make sure to go to second calculate now, because we're making our calculator do the work for us. Second trace, which is calculate. Go to maximize, which I think is 4. And make sure to put that little star, edge over, and make it blink on the left side of the hump or the hill. Max, and we're maximizing. Hit enter, because it's asking us for the left bound. You got to be on the left side of the highest point. Hit enter, and it says, okay, give me the right bound. So go over and make the star blink on the other side. Hit enter again. And when you do that, it'll ask you to make a guess. Don't make a guess. Just have it do its work. Hit enter again. And you find out that it gives you the maximum R value, or the point, at 1.825.
How did you do that?
Yeah, I'm very lost.
So everybody hopefully found 1.825 for X, which is what we're calling R. We also, if you're looking at that screen, I think it came out with like a 19.1 something.
Yes, it was 19.1.
19.1. The 19.1 represents the maximum volume. Right? Because guys, our equation was asking us to find the volume, or to use the volume equation to maximize it. So this 19.1 is the maximum volume when you let R equal 1.825. Here's the thing. The question never asks us what is the maximum volume. It wants to know what R value makes it the maximum and what, that's R, H value. Because look at here, it says radius and height. Here's the cool thing. If I know that this R value is what makes it have the biggest volume, I can use that I solved for H already in terms of R to solve for H. So I will then just say H is equal to 10 minus 1.825 squared over 2 times 1.825. And I could tell you then that the H value is what? You guys hopefully found that H ends up coming out to 1.827, aka almost exactly the same height as or the same value as the radius.
I did not get that.
Check your numbers if you're not getting that. So, what does this mean about our can? Our can has a radius that's the same as the height. Remember, a radius is only half the width of a can. So really when it comes down to it, your can is going to be twice as tall as height. So the can would be twice as tall as it is, or wide, sorry, as tall. So it's almost like, when I'm thinking of, it looks more like a tuna can. Tuna cans are wider than it is taller. Okay? This also has implications, the fact that what if this company only had so much material to make this can, and they still wanted to maximize their volume. Okay? They want to make the biggest glass candle holder they can with only so much glass. The last thing we're going to talk about is average rate of change. Guys, when we talked about average rate of change up to probably now, it's always been of lines, linear functions. And if you took the rate of change of a line, it was always the same. It was constant. And it was something we called slope. And so today, we're going to mix it up. We're going to talk about nonlinear functions. And you still can find, aka the slope, the rate of change, but it has to be over a given interval, and it will be different over every interval. So what I'm saying is that if I had this, even the function that's in this diagram here, this graph, they're choosing this point and that point. And what they're doing is they're just finding the slope, aka rate of change between those 2 points. Does that slope give you a good representation of what the actual slope of that particular function? No. But over the fact of x1 to x2, the slope is going down, but you can tell that that function is decreasing. And so we call the line that you can connect those 2 points a secant. I'm not hung up on that. Okay? I'm not worrying about that part. I'm worrying about the part that says this thing, the formula. They're saying that the average rate of change, guys, from x1 to x2 is just f of x2 minus f of x1 divided by x2 minus x1. F of x2 and f of x1. That's a fancy way of saying what? It's a y value. It's a y value from point 2, so we would call that y2 minus y1 over x2 minus x1, aka you're just finding slope. Just find the slope between 2 points, an interval. So what they're not doing is they're not telling you the points directly. They're not going to say, use 1, 2, and 5, 7. They will tell you, here's a function, here's an equation, from x here to x there, what is the slope, average rate of change? So, rule of thumb. if the average rate of change is positive, that means the function is getting taller. It's getting bigger. Its slope's bigger. If the slope's going up. So what we're going to do here is we are going to find the average rate of change for part A. F of x equals x cubed minus 2x squared minus 3x plus 2 on the interval from 2 to 3. So here's the cool thing. When it says from 2 to 3, it tells you x1 and x2. 2 and 3. So all I need to do is put the formula down and fill it in. What was the average rate of change formula again?
Fx with 2 minus fx1 divided by x2 minus.
Right. Do you know x2?
3,
Do you know x1?
2.
Do you know f of x2? F of x1? No. But can you find them? And what does it mean to be f of x? Or f of x1? F of x1 is f of, wait, what was x1? 2. Oh, what does it mean to be f of 2? It means to evaluate the function at 2. So, what's 2 to the third power? 8. What is 2 squared? Times that by negative 2, which would be a negative 8. Interesting. And negative 3 times 2? Minus 6 plus 2. These cancel away, leaving you with? Negative 4. What's f of x2? That'd be f of 3. What's 3 cubed? 27. What is 3 squared? Times negative 3. Or times negative 2, sorry. 9 times negative 2? Negative 18.
Yeah.
And negative 3 times 3? Minus 9 plus 2. All of that cancels each other, leaving you with? 2. Can you now fill in the formula? Do you know f of x1? F of x2, x1, and x2? Okay, fill in the formula, guys. F of x2 is 2. F of x1 minus negative 4. What's x2? 3 minus 2. What happens when you subtract a negative, guys? Add. So 6 over 1. The average rate of change, aka the slope between x1 and x2, is 6. This function is increasing from 2 to 3. The same thing can apply for part B. That should be f of x, not f9x. So I'm not going to do that problem because I think it's just plugging in the values, figuring that out. We probably won't have enough time for this one. But it's the same thing. Again, real life type of situation. Talks about wind resistance not mattering. But when I drop an object, it falls at 16t squared with t's in seconds. So I need to find f of 2 and f of 4. And then do the average rate of change. Guys, homework for day 2 is page 40, 33 through 36, 54 through 59. Have a great day.